All right, so we've done the PD part. What we need to do now is do the PI part. So the PD has gotten us such that we have a overshoot of 20%. It's great. And we've reduced our peak time to 2/3 of what it was. That is cool. But we still have steady state error, right? We still have this response here. Steady state is 0.85, and we are telling it to go to a value of 1, right? For a step response, we're inputting a bunch of 1s for our R of S, right? And looks like our C of S is ending up at 0.8 something. So there's an obvious steady state error of 0.15. We don't want that. We want it to go to the 1. So we're going to add a PI controller and then multiply that PI controller by our PD controller and obtain a PID controller. So what we're going to do is essentially add a 0 and then divide that by an S. So we want the 0 to be small. Here's the form. We have the P term, same as before, our proportional integrator term, sorry, just our integrator term here, that gain, and then we are going to do 1 over S instead of S. Right, for our D, we had KD times S. For our integration, we do KI over S, because 1 over S is integrating, right? So if we're inputting our error, this 1 over S term will integrate the error. Great, so doing some math, we end up with this form here. This is so that way we can clearly see what our 0 is. It's going to be negative Ki over Kp, and then we have this fixed pole at S equals 0. And that's always the case whenever you integrate, because you're just going 1 over 0, right? So you're going to have some pole at S equals 0. So we're going to choose our PI controller to look like this. So our Ki over Kp is going to be 0.5. We want it to be small because we've gotten pretty much where we want to be in terms of overshoot and peak time. We don't want to change the system too much, so we pick a small 0. What we really want is this 1 over S, because this will integrate the error away, and we'll get a 0 steady state error. Cool, so assuming this, we can then multiply this PI controller by our PD controller that we found before, and we get this thing here. So we have two zeros, this one at 0.5 that we've just chosen because it's small, and this one at negative 57, and that one we found. That one was a little bit more intensive, right, from the PD controller. We had to use the root locus for that. And a 1 over S, which integrates the error away, so we get 0 steady state error. So all we need to do is figure out what this K term is, right? So we have made it possible via our zeros and our pole, so that way we get a overshoot of 20%, a peak time of 2/3 of the uncompensated system, and we're going to get 0 steady state error. So here's our current controller. This is just our PD controller with a 0 at negative 57. We're going to add another 0, real 0 at negative 0.5, right? That's from our PI controller. And then we're also going to add a real pole at 0. That's the 1 over S. Okay, so what this has done to our root locus, you can see that our PI, multiplied by PI, has shifted our root locus away from this intersection point by a little bit. That's okay. We're close enough. We can just kind of approximate. But you can get nitty-gritty if you want to, move some zeros around, redo the whole thing, kind of iterate like that. We're going to say this is fine. So what is this value? What's our k, right? What is our k so that we get our poles right over here? Let's go to, what did I get before? 4.6. That's, close enough. I don't want to go any higher because then you end up going over this overshoot. So I'll just keep it at that, 4.6. And you can kind of tell, just how accurate we're getting here. Pretty accurate, but not exact, just a little bit away from the intersection. So let's look at our response. This is great. Real good response here. We've got a overshoot of 15%. I can see by that amplitude here, right? So our steady state is 1, so we have 15% overshoot. We wanted less than 20. We have a peak time of 0.194. We wanted 0.2, so this is great. It's less than that. And our steady state value, if you continue this on past 4 seconds, right, it approaches 1. So that's great. It has 0 steady state error. And so we figured out what our gain is, right, that 4.6 from our root locus, right? Really important that you guys realize that that's what this parameter term, right? Not the 0, but this parameter term. That's what you move. That's what you use to move the poles, or that exact point that you're looking at the root locus. If you don't specify that, you don't know what your roots are. You don't know where you're looking at. Your system isn't defined. You need to specify this term here to say, okay, we're looking at this intersection, right? That's what these pink dots are doing. Anyway, so we figured out what these are. And we can multiply them out and get our K1, K2, and K3. And so I get pretty much what Professor Ayubi got, and that's great. So any questions, please email me. We have this other example right here. And I'm going to figure that out tomorrow. I have some questions to ask. Okay. See you guys in part 3.